Good afternoon.
You beat me to it today.
Well, mission
How is
accomplished.
everyone?
Very good. Okay, I guess.
So did anyone do anything amazing over the weekend?
I got my first plant.
Your first plant? You mean for like your room?
Yeah. Yep.
Okay. So I guess, that's like step one, get a plant, maybe step two, a pet, step three, a boyfriend, something like that. Is that how it goes? You're not going to say? Oh, wait. Open up the wrong class. Okay, let's try this again. All right, so let's see. Everyone's there in Mogollon. Everybody's there in Winslow. I think everybody's there at St. John's. So we're good. That's awesome. That makes taking attendance much easier. Hey, Chloe.
Yeah.
I have a question for you. Did you happen to look at your attendance grade like before and after I updated?
Yeah. I think it went up. It went up
Okay.
like a couple points.
Yeah. See, here's the thing. I also noticed that. See what happens when I create the shell for the calculus class is it uses the dates and times from the last time I taught it. Anyway, so to make a long story short, I was curious as I looked. See, every at the beginning of every week, I've been having to delete dates of attendance that we don't do. So anyway, the computer would generate like that as if this class met 8 times a week. And so I've been just deleting them every week, the extra ones, and it just generates it. So, but I got to thinking as you were doing your percentages and so on Friday, that I thought maybe it would make a difference for you if I deleted all the rest of those dates for the rest of the semester. And so I did, and so in the hopes that it would actually bump that attendance percentage up. Does that make sense?
Yeah, and then you just add them back in. Is that what you're saying?
Yeah, so that way, instead of saying that you've attended, 20 times out of 160, it'd be 20 times out of, 50 or something. Anyway, I don't know what the numbers are, but so I deleted all those extra ones. I was just curious if you did notice a bump in the grade.
It went up like 1%. So one and a
Okay,
half.
so maybe that could have just been when I updated the fact that you watched the video.
Yeah.
So
That might have just been it.
So I don't know. Anyway, I was just kind of curious to see if that would matter. But all
Thank you
right.
for doing that.
Oh, sure, no problem. And did you get have you read my other email?
I just read that about 3 minutes ago. And we did
Okay.
make those plans before, but if you can't excuse it, I understand.
No, that's kind of where, because see, I feel like, and I was actually going to talk to you guys about breaks, fall breaks, and that kind of stuff. Is that if to me, like if your school is on fall break, and let's say you ride the bus into school, and the bus, I mean, most of you guys probably are in town. Maybe that's not a big deal. But if you were a bus rider and you have no transportation to school and your parents say they can't bring you or whatever, and you make an effort, then to me, I consider that like it's not your fault at that point in time if you were to miss. And so then I would allow you to make that up. And see, like in this situation with you, where you're going to be gone, I kind of know what that's like. And you really, you personally didn't have really any choice in that. and especially if the plans were made before you even signed it for the class. And so I feel like that the fact that the school is taking those days off, that's really not on you. And so I'll let you make those up.
Okay, thank you. And I'll be here tomorrow, just not Wednesday or Thursday.
Okay, all right,
Okay.
great. All right, so Winslow, you guys are on fall break this week?
Yes.
Oh, okay, all right. Well, I appreciate you being here today. All right. So, does anyone else have any? So did anybody do anything amazing over the weekend?
This isn't really amazing, but we painted the biggest room in my house.
Oh yeah. So that would be like your bedroom.
No, I wish.
Oh come on! I kind of believe that you're like the favorite in the family, so you probably get the master suite, and right?
No.
What?
No, I'm the oldest, so I'm the one who gets all the responsibility, but not really the favorite.
Yeah.
We're all kind of favorites. It's
Just
our main room with the kitchen, the dining room, and stuff.
Just remember, with great power comes great responsibility. Okay.
Yep.
So anyway, you know where that saying comes from, right?
Uncle Ben.
What?
She said Uncle Ben.
Uncle Ben, very good, very good. Okay, well, yeah, you just 1 point with me there, Jordan. So good job. All right, so we are on 3.2, and let's see. Oh, I wanted to look up something really quick. Okay. Okay. So, okay, so, oh, right. So we haven't taken the quiz on 2.6 yet. So then, okay, so we're going to do the quiz on 2.6 and then probably 3.1. And then, assuming we finish 3.2 today, then we'll do 3.2. If we don't finish 3.2 today, then it'll be 2.6 and 3.1. And then we'll take the chapter 2 test the following Wednesday. Okay? All right, so that's kind of the plan. All right.
Can you say what we're taking this week one more time, please?
So this week, we're going to do quiz 2.6. 2.6, 3.1, and then if we finish 3.2 today, then we will take 3.2. If we don't finish 3.2 today, then that will be pushed back. And then next Wednesday, we will take the chapter 2 test. Okay. All right.
Could Skylar and I take those quizzes tomorrow after
Sure.
or before class maybe or something?
Sure.
So I'll be here.
Talk to Miss Lopez and let me know.
Okay.
That'll work.
What's out best for you guys.
Okay.
Okay.
Thank you.
You bet. Okay. So, all right. So we were on part 2. This alternative formula for the derivative. Okay. Now, let me just say the formula that I use. Oh, I forgot to switch the camera. The formula that I use is the one that we did last time. The f of x plus h minus f of x over h. This is an alternative formula, and I'm going to just tell you the only time I ever used it is just teaching this example. All right, and so there's like on the practice problem, I say use the alternative formula, and I found that like maybe 5% of students like it better. So, there might be one of you that like it better. So I'm going to go ahead and teach it. But if you don't like this formula better than what we've been doing with the definition of the derivative, then you don't need to worry about it. Okay? This is just another way to do it. Okay? So the alternative formula for the derivative, f prime of x, is the limit as z approaches x of the f of z minus f of x divided by z minus x. So there's no h in here. It's kind of like saying the two different y's over the two different x's. So some people like it because it looks more like the slope formula, and then the idea is as the first point is approaching the second point, as z approaches x. Okay, so let me just kind of show you what so we did that already. Okay, so let's say we have f of x equals radical x, and x is greater than 0, so that we don't have any complex numbers here. So then the f of z, you just plug in the z in place of the x, so you get radical z. So then plugging it into the derivative formula, we get the limit as z approaches x of the square root of z minus the square root of x over z minus x. Okay? All right, now, for this one, you might remember that a lot of times what we've done at this point is multiply by the conjugate, and that would still work, but I'm actually going to show you this new algebra trick on this one, okay? Just so that this example is worthwhile to me, is so here what you do is we normally don't think of z minus x as being factorable, okay? But because of this numerator is the square root of each of these. So the algebra trick is this, and I know you've never seen this before, is that you actually factor z minus x to radical z minus radical x times radical z plus radical x. So I know you've never factored like that, but since we need square roots anyway, you think of z as radical z squared and x as radical x squared, and then this becomes the difference of two squares. All right, so then radical z minus radical x cancels, and so you get 1 over radical z plus radical x. And now if you plug in x for z, then you get 1 over radical x plus radical x would be 1 over 2 radical x. And so that's the derivative. Now, if we wanted to find the derivative at a certain point at like x equals 3, then I would plug in 3 at this point, okay? Or I could plug in 3 for x at the beginning, and it would still work out, okay? All right, so go ahead and try practice 2. And so I'm asking you to find the derivative of one similar to this, and then I'm also giving you an x value at x equals 1. And so you can plug that 1 for x in the beginning or at the end. All right. Joey, what do you have?
Okay, I'm not really sure. I got to where I had radical z minus radical x over z minus x.
Okay, so then the z minus x, you can factor that to radical z plus x times radical z minus x. So that's the new algebra trick.
Okay.
And then you can cancel the numerator.
Could you move it up a little bit, please?
Sure. All right, so Joey, what'd you get for your final answer?
1 over 2.
Yep. Okay. All right, so when you go through it, see that like the 2's cancel, you do your little factoring trick, and you end up with the same answer that we got in the example, 1 over 2 radical x. And so then when you plug in 1 for x, you get the square root of 1 is 1, so you just get 1/2 for the derivative or the slope of the tangent. Okay?
Mr. Strong, can you go up?
Yep. So here's the f of x. So here's the f of z. And so you're doing the limit as z approaches x of the f of z minus the f of x over z minus x. Then you distribute the negative, and then the 2's cancel. All right? Any questions on that? Okay. Okay. So, so it says there are many ways to denote the derivative of a function. So that's f prime of x, y prime, and dy dx. These are the ones that are the most common. I would say we use one of these three like 90% of the time, maybe 99% of the time. These other ones, df of x, df dx, df of x dx, just a particular book might show those in a problem, but these are the three ways that we do it. Okay? All right, so next, graphing the derivative. What can we learn from the graph of y equals the derivative, f prime of x? All right, so we can learn if the rate of change of the graph is positive, negative, or zero. We can learn the growth rate, where the rate of change is increasing or decreasing. All right? All right, so remember when we're looking at the derivative, we're looking at the slope, okay? So this graph up here in blue is the original function, f of x, okay? Down here in red, I'm graphing the derivative, okay? So let's just see how that works. Okay, so up here at point A, where we would have a horizontal tangent, then there the slope is going to be 0. So if you come down here at A prime, it's going to be equal to 0. All right, then at point B, we get -1. Now, how are we getting -1 here? Well, to get these slopes, we're just kind of approximating. This -1, a slope of -1, means that you go down 1 over 1. It's down 45 degrees. So that would be at -1. So if you come down here at B prime, on the derivative graph, we're at -1. The slope is -1. For point C, it's actually even more negative. It's steeper. Now, -4/3, I don't know how you would get that exactly. You're just eyeballing it. But it's steeper. So that means it's more negative at C prime than B prime. Okay, then at point D, the slope is 0 again. It levels off. So you have a horizontal tangent. So back up here at D prime, the slope is 0. And then for E, okay, they're saying, well, if you're just going to estimate, so you imagine a tangent line here, you would go up 4 and over 2, so that would be, or excuse me, up 8 and over 4, so that would be a slope of 2. And so we come up here, so E prime would be, the slope would be 2. And so here, again, looking at the derivative graph, this slope is 0, then it goes negative, then back to 0, and then the slope is positive. Okay, so now let's see if you can interpret this graph. Okay, so it says, use the graph for example 3. So I'm going to go back to example 3. Where is the rate of change? Now, not the function itself, but where is the rate of change, positive, negative, or 0? Okay. Where is the rate of change, positive, negative, or zero. All right, so Hannah W., where is the rate of change positive?
Just E.
From point D to E. So because here the rate of change, so you can look at the slope graph and see it's above the x-axis. So the slope is positive from D prime on. Or here, from as it's going up, where you see the graph increasing, then the slope is going to be positive, or the rate of change is positive. So you would say from D to infinity, it's going up. Okay? All right, next, where is the rate of change or slope negative? Joey.
From A to C.
From A to C, very good. See, from A to C, the graph is, actually, it's going down from
A to D,
to
right?
D. From
Okay.
A to D. And so the derivative, looking at the derivative graph, the slope is negative. It's below the x-axis from A prime to D prime. You actually, before A prime, it's also negative. So you might even say from negative infinity to D. Okay? Although or at least from negative infinity to A and then A to D. Okay? Let's see. Where is the rate of change or the slope zero? All right, David.
Would it be at point A or at point D?
Yes, that's right. So you can tell here, well, here it says the slope is zero here and here. Looking at the slope graph, the slope is equal to zero here at A and D. Okay, good. Okay, what is the rate of change of f at x equals 5? What is the rate of change of f at x equals 5? Rhett?
-4/3.
That's it. So you go over x equals 5, that's point C, and the slope or rate of change is -4/3. Okay? So this is all just about interpreting the graph.
Mr. Strong,
Yes.
how would you write, so for the question A, how would you write where it goes from like positive to negative?
Okay, so I said it's positive from D to infinity, negative from A to D. You might also, like I said, include from negative infinity to A to just get that last little loop. And then it's zero at the points A and D. Does that make sense, or do I need to go back to the graph?
That's good. Thank you.
Sure. All right, and then the rate of change of f at x equals 5 is -4/3. And then where is the rate of change itself increasing or decreasing? All right, let's go back to the graph. So where is the rate of change itself increasing or decreasing? Let's start with increasing. So where is the rate of change or the slope increasing, Dana?
E to infinity.
Okay. Well, that's for sure. How about from D? How about at C? See where this graph is increasing. Imagine if you were a runner along this path. Where you're going uphill, that's where the graph is increasing. So from C to infinity, and where else are you going uphill? Go ahead.
Negative infinity to A.
Negative infinity to A. So this little bit you're going uphill, and this bit right here from C to infinity. Okay, so where are you going downhill? Where is the rate of change of the slope decreasing? All right, Nathan.
A to C.
A to C. Excellent. All right, any questions on that? So here's one application of the rate of change, okay? So you might not know this, but if you are diabetic and you're a pilot for a commercial airline, you have to monitor your blood sugar very closely, okay? So like here, this is showing the blood sugar of a pilot during the flight. He's going from two different islands in the Mediterranean Sea, from Crete to Santorini. Okay, and so as he's measuring the blood sugar, see the slope of each of these is the change. And so as we look and we graph the slope, see here they're just little linear intervals. And so we can calculate the slope, the difference in y's over the difference in x's. So that would be, here it would be like from 78 to 92 or something. So maybe 14 over 1. So 14. And then it goes a little tiny bit steeper. And so the slope climbs up to 15. And then it starts going down. The slope is about what, 2? Oh, it goes actually negative for these 2 hours. So the slope's negative, and then so you can use this, and so they have different guidelines in their manual that that not only do you have to be within a range, but you can't have it be changing too fast. So I don't know if any of you have ever had problems with your blood sugar, but if it rises too quickly, if it spikes or it drops too quickly, if it bottoms out, you can actually have difficulties either way. Okay, and so pilots or engineers, people that are especially that are in a situation where they can't be passing out or whatever, it's very important that they monitor what's going on. So have any of you ever had to monitor yours or somebody else's blood sugar? What do you think happens, or what do you think happened here after 2 hours? To make so the blood sugar is rising, then all of a sudden it starts going down. Any idea what happened there?
Was it an altitude change?
Well, altitude does have some effect on your blood sugar, but it wouldn't be quite that steep at 2 hours. Okay. More likely, what happened there is he took some insulin or something, and or some kind of medicine, and it started dropping his blood sugar. And then right here, see, he starts to worry about it dropping so too fast. And because if it drops too fast, you can have problems. I actually had a student once that went into like a diabetic seizure in the class. It was kind of scary, but fortunately, you know what helped is that her classmates knew what was going on. Because this was a college class and she was taking classes with some of her former high school friends. And so they were aware of what was going on. And so, because I thought it might be like epilepsy or something. But anyway, it was a diabetic seizure and we were able to take care of it without any problem. So, all right, well, that's just an application of, I just kind of wanted to throw that out there. All right, differentiable on an interval, one-sided derivatives. Right and left-hand derivatives may be defined at each point in the interval. So if you have a graph and you can calculate as h is approaching 0 from the left, then that would be the derivative. As h is approaching 0 from the right, then that would be its right-hand derivative. So just like you have left and right-hand limits, you can have left and right-hand derivatives. Okay, now, so with an absolute value, remember I told you that you can actually divide the absolute value function up into two piecewise functions. Well, for the left-hand side, the slope is -1. So its derivative is -1. For the right-hand side, the slope is +1. So what that means is the derivative is not defined at x equals 0 because the right hand and the left hand derivatives don't match. Okay? So then, so that point says the function y equals the absolute value of x is not differentiable at the origin where the graph has a corner. Or in other words, at the vertex is where the absolute function is never differentiable. So you can put at the corner or at the vertex. It's not going to have a derivative there. All right? So I want you to see if you can figure out where is this function not differentiable. All right, Hannah Z, what do you think?
At x equals -2.
At x equals -2. Why not? Why is it not differentiable there?
Because that's where the vertex is.
That's it. That's where the vertex is. So we just said at x equals -2, that's where the vertex is, and so the absolute value functions are not differentiable at their vertices. All right, so good job, Hannah. Okay, vertical tangents. Since the slopes of secant lines joining the origin to the points on the graph as on the graph approach infinity, the graph has a vertical tangent. A radical function is never differentiable where the radicand equals 0. So at this endpoint, it's not differentiable there because there's no left-handed limit. The function isn't defined to the left.
Mr. Strong,
Yes.
we missed a line. The derivatives at endpoints are. Is that needed, or are we going to cover that?
The derivatives at endpoints are not differentiable. Let's see, I kind of was talking about that there. Let's see if I just missed that. Yeah, because they're one-sided limits. So since they're just one-sided limits, they're not differentiable because on both sides. So we would say the derivative doesn't exist at that point. So it just exists on one side. Okay. So typically though, I'm not going to ask you questions about the endpoint. Okay. All right. So if I said, where is this function differentiable? Okay, so even though it's defined from 0 to infinity, you wouldn't include 0 because at the end point, it doesn't have a left side to it. And so you would just say it's differentiable from 0 with a parentheses from there to infinity. Okay. All right, so let's try the next one. So where is that differentiable? All right, so Joram, where do you think?
From 4 to infinity.
From 4 to infinity, because it's this minus 4 inside here moves it over 4, and so just from 4 to infinity. So if I said, what's the domain, then you would have a bracket on 4. But where is it differentiable? You have a parentheses on 4 because 4 itself is not included. Okay. All right. So then the question is, where is a function not have a derivative at a point? Okay. And we're going to talk more about all of these. But for right now, if you just want to write these down at a corner, so like the absolute value, at a cusp. So a cusp is like how you used to draw birds, like in the 3rd grade. That's a cusp. At a vertical tangent, so when the graph goes almost vertical and the tangent would be vertical, or at a discontinuity. Those are the points where the derivative is not going to exist. All right, any questions on that? And the last little bit of notes here. Oh, this is an example of each of those. Okay, So if a derivative at x equals a constant, then if the derivative is equal to c, then f is continuous at x equals c. Okay? So if the derivative exists at a point, then the function is continuous at that point. Okay? But the inverse of that is not true. If a function does not have a derivative, then the function is not continuous. That's not true, because like the absolute value, okay, it doesn't have a derivative there, but it's continuous. Okay? The converse of that statement, that's where you switch the if and the then. Okay? If f is continuous, then does f have a derivative? That's also false. And again, the absolute value is the counterexample. See, this is continuous, but it does not have a derivative at the vertex. Okay? Then finally, the contrapositive is true. If f is not continuous, then f does not have a derivative. That's where you switch the if and then and negate it. That's how you get the contrapositive. That is true. So if it's not continuous, so you draw something that's not continuous, then it can't have a derivative there. So that one is true. So the original statement and the contrapositive are logically equivalent. Okay, so we're going to stop there, 3-2. So then if you have questions, you can ask them tomorrow on 3-2. So I'm going to plan on doing the quiz on 2-6, 3-1, and 3-2 on Wednesday. So Chloe, Skylar, have you guys worked out when you want to do it tomorrow?
We can do it right after class tomorrow. I
Right
think Miss
after
Flip
class.
has
Okay,
emailed
that'd
me.
be great, because that way, if you have any questions, especially on 3-2 or any of it, you can ask during class.
Okay,
tomorrow.
thank you.
All right, great. All right. I'll write that down right now. So you guys have a great day, and we'll see you tomorrow. Thanks for working hard.